We are live. Um, all right. If you can, hear me, see me, if everything's working fine on that end, just drop something in the chat, maybe a 1 through 5, based on how you're feeling about AP Chem right now. Just something to let me know. You can hear me, see me, all that stuff is working out. 1, okay. All right. Perfect, looks like everything's working. So really, tonight is really just like an AMA, right? It's an opportunity for you to ask me literally anything you want about chemistry, AP chemistry, and really any topic. I know we're probably all in different spots depending on where we are in class right now, especially with the changes to the curriculum from last year. But if you have any questions regarding really anything in chemistry, feel free to just spam me with as many questions as you possibly can. So I'll just kind of, hey Brandon, so I'll kind of just open it up for a minute or two, just let you guys get your first couple questions out. If you want, you can either drop them in the chat because we kind of have a smaller crowd tonight, or if you want to drop them in the ask a question area, that also works so that we can keep track of what questions have and haven't been answered and stuff. But yeah, literally any question about chemistry is fine. If it's about from the most basic of things in chemistry to the most advanced topics at the end of the course, I'm happy to answer anything. Could you explain how to solve partial pressures of gases? Sure, yeah. All right, so I'm going to just pull up an online whiteboard that I use just because it's really helpful. Where is it? There it is. Okay, so basically what the law of partial pressures says is that if you have a gas, right, with some mixture of gases, right, if you have, let's say you have some oxygen in here, you've got some water vapor, maybe you've got some hydrogen gas, right? Basically what the law of partial pressure says is that the total pressure in this like, I don't know, beaker, whatever it is, I mean, but in this beaker is equal to the partial pressure of oxygen plus the partial pressure of water plus the partial pressure of H2, right? So basically it's just adding up the partial pressures of each of the constituent gases and then figuring out from there. So basically, the way to solve for like a specific partial pressure is there's a formula, and I'm Googling it right now just to make sure I don't screw it up. Let me see. Trying to find it now. Here we go. So it is, where is it? Trying to find it. And okay, so it basically is, so the partial pressure of some element A or some compound A is equal to the mole fraction of gas A, I'll get into that, times the total pressure, so times this P total, right? And what this mole fraction is basically, it's the number of moles of A, right, over the total moles. Here, let me write that in. Right, so basically, I mean, it kind of makes sense pretty logically when you look at it, right? It makes sense that depending on if there's more or less of that gas, it'll have more or less of an effect on the total the total and partial pressure. So, for example, if we have in here, let's say we have 3 moles of oxygen, O2 gas, I don't know, 5 moles of water, and then 4 moles of H2, right? And let's say that this total pressure is 7 atmospheres. I know that I'm kind of making up numbers here, but this is an example of a type of problem that you could get. So for example, the partial pressure of oxygen here would equal the mole fraction. So it would be 3 over, 3 plus 4 is 7, plus 5 is 12, right? Times the total pressure, so 7, right? Which will then give us, what's that, 1/4 times 7, which is equal to 7/4 atmospheres. So that's like an example of when you'll need to apply the law of partial pressures using gases. So basically this formula, and then just understanding that the total pressure in a beaker or wherever you have gas is equal to the addition of the partial pressures of all of the gases in that container. All right. Right, so does that make sense, Dakota, just kind of how the way I explained it, or do you have any more questions? Perfect. All right. Let me just erase this real quick. We got another question. All right. What is Coulomb's law? All right. That's actually a really good question because Coulomb's law is a topic that comes up pretty frequently on the exam. So Coulomb's law, I'll just write out the formula first. It basically says that the electrostatic force is equal to the charge of the two bodies over their distance, or their, in terms of like atoms and ions, their radii squared. So I know this might look really really scary because you don't really know what all these letters are. There we go. Right. Oh, and there's also there's a constant there. But really, well, all this tells you, and you won't ever need to plug into this formula for AP chemistry. You only need to know how to apply this formula specifically qualitatively. For example, I have this ion and this ion, and this radius, this ion, and this radius, which will have a higher force. So really what this tells us is that if we want high attraction between ions, we want really high charges, right? That's handwriting for you. High charges, and we want a low, we want small atoms. Oh my God, my brother's screaming at me to get off the Wi-Fi. I can't get off the Wi-Fi, Jamie. So yeah, so really, for example, let me pull up a periodic table. And really, when you're doing chemistry questions, I really highly recommend that you use a periodic table, more for the sense of you have it during the exam, and it's the most invaluable tool in chemistry. So for example, let's look at lithium fluoride, right, versus something like, I'm having to come up with this on the spot, beryllium fluoride, okay? There you go. Right, so we know, so really this is the type of question they'll ask you involving Coulomb's law. They give you, maybe two ionic compounds, and they say which one has the strongest attraction and why. Or they might ask which of these four has the strongest attraction, right? And that attraction is known as lattice energy. It's basically how forceful the attraction is between two ions in an ionic compound, and it helps define a lot of like the energetic properties of ionic compounds. So let's take a look at this, right? So we have lithium fluoride. So we have lithium with a +1 charge and fluorine with a -1 charge, versus beryllium fluoride, where we have a 2+ charge and a 1- charge, right, on the fluoride. And the thing is, beryllium is actually smaller than lithium. So really, beryllium fluoride has got both of the things going for it. So it's going to have a much higher attraction to its atoms than will lithium fluoride, right? And so it's really just a matter of high charges, small atoms. If you have something like, francium iodide, it's really not going to be that strong because you have just one charge and the biggest atoms on the chart. So it really has to do with, it has to do with those two properties of ionic compounds. So yeah, if that doesn't make sense, feel free to ask your question again, and I'll, try to clarify. All right, what are some resources? What resources do you recommend to study for the AP chemistry exam? All right, that's a really good question. Here, I'm gonna make myself big again. There we go. So that's a really good question. I personally, I say this in every stream where someone asks me this, I'm not a review book type of person. I'm not someone who is able really to look at a textbook and just read for hours on end. I'm not that person. If you are that person, that's fantastic. It's really up to you. I mean, there's tons of resources out there. There are YouTube channels like Organic Chemistry Tutor and a bunch of others. Tyler DeWitt is a good one. And then there's also, I know there are some teachers out there who make lectures. So if you kind of dig far enough, you'll find just full-on lecture sets. Actually, there's one for one of the textbooks. If I can find it, I'll drop it in the chat through this stream. I can't quite remember what it is now, but I'll drop it. Really, it's up to you. I mean, a lot of people kind of wonder, oh, how did you study? But really, how I study didn't matter because the way I study isn't the way you're going to study, because of the fact that we're two different people, right? You might really hate watching lectures and, watching videos and learning that way, whereas I might really hate reading a textbook. I mean, I still have my review book sitting there, barely touched because of the fact that I wasn't able to use it. and that's why I'm not buying review books again this year. And so really it's up to you. I mean, I personally liked lectures online, but it's really up to you. All right. We'll give another minute or two for y'all to think of questions. And then if not, I'll kind of just start talking about, you know, my experience in chem and everything else. Here we go. Here we go. All right. How do I calculate electrochemical cell potential? Oh, geez, we're getting into like electrochem. Okay. This is kind of a really more advanced topic. So for those of you who haven't covered this yet, don't worry. Here, I'm going to just pull a picture because I don't want to have to draw this out. One sec. All right, so let me just find an example so that I can actually, because I'm too lazy to actually find a good one to calculate. Here we go. So I know this probably to some of you guys might look really scary. So this is what a galvanic cell is. It's basically a way that we get electrons to flow through a wire. And there's also another component here called a salt bridge that goes like that. So basically, the way you want to find the actual cell potential for an electrochemical cell, such as this galvanic cell, is the first thing you want to do is you want to write out the half equations of what is going on. So we see that lithium is losing, or not lithium, I can talk. Zinc is losing 2 electrons, right? So we are, right? Zinc is getting oxidized, right, into zinc 2+, and it's losing 2 electrons. And then we see copper is, we see that copper 2+ is getting reduced to form by 2 electrons to form copper again, right? So the way we really find the numbers for a question like this is we want to look at something called a reduction potentials chart, right? So some of you might see this in your AP Chem classes, like earlier in the year, as like an activity series. When you get to later in the year, when you study electrochemistry more in detail, you're going to really be using exclusively these charts, right? Because of the fact they show the energy changes and the electricity potential of these, things. So we take a look and we see that first we find the reduction potential for copper 2+ getting reduced to form copper, right? So this has a reduction potential, E0 it's called, of 0.34, right? And then we go down and we look for zinc, right? Well, we see that zinc isn't here, right? We can look and look, and we're not going to find zinc because what this isn't a reduction. This is an oxidation. So we actually want to look for zinc 2+, which you can find right here. And so we see that this has a reduction potential of negative 0.76. And so what we're going to do is, because we have an oxidation here, is we're going to flip the sign on the reduction potential. So we're going to get that E0 here is equal to 0.76. Then essentially what you do is you're going to add the equations together in order to get your full cell potential. So you get your full equation, right? These electrons will cancel out, and you'll get that zinc and copper 2+ react to form zinc 2+ and copper, right? It's just that electron transfer from here to here with an E0 of, what is that going to be, like 1.11? I'll plug it into a calculator. 76 plus 0.34 is 1.1, right? So that's equal to 1.10 volts, right? So that's really how you would do it for something like a galvanic cell. It's just using this chart to find values and then to find an actual voltage, right? So does that make sense? All right, perfect. All right, any other questions, comments, concerns with AP Chemistry, even just about the test, the exam, preparing for the exam, even my experience in AP Chem, since for those of you who know me in real life, the teacher for AP Chem at my school is something else. So just, feel free to ask literally any question. It can be the most basic question out there, all the way to, you know, what someone just asked, which was basically an end of the course topic. So I'll kind of wait another little while. And then if not another minute or two, I'll kind of start talking about, you know, my experience with AP Chem, right? All right, I guess in the meantime, I'll just talk about, you know, what AP Chem was like for me. So really, for me, AP Chem was a different kind of course because of the fact that my teacher didn't really teach. I guess that's kind of not the best way to phrase it. Basically, the way he taught was he had lectures on his website, and our homework would be to read them or watch them. You don't read lectures. Watch them and then take notes. So by the end of the year, I had a notebook filled to the brim of just pure chemistry notes, right? So really, this was kind of all I had to rely on, since all of our time in class was spent doing problems, labs. We really didn't have much time to go over lessons, right? And if we had any questions, we had to go to him on our own time. So really, you know, in AP Chem for me, it was really a heavily self-guided course, especially because I got ahead of the game and kind of started watching the lectures ahead of time. And so that's really something I'd recommend to those of you who have a teacher who kind of teaches like that, is to start watching the lectures just ahead of time, so that when you walk into class, it's not like, oh, you watched this, you know, yesterday. All right, here's a question. I'm try to add that as a question if that'll work. There we go. All right. To explain how to identify the intermolecular forces in a compound. Sure. Okay, so really when we're talking about intermolecular forces, there are a couple major ones that we're going to be dealing with. So there's ion-ion, right? There's ion-dipole, dipole-dipole, and then I'm just going to write these as DD. There is hydrogen bonding, which is a special kind of dipole-dipole interaction. Then there is London dispersion forces, right? LDFs, as they're called. Right, and so I'll kind of go in depth into each of these types and kind of talk about them. So starting with ion-ion forces, you know, they're kind of exactly what you would expect them to be. They are the electrostatic forces between two ions. So we see, you know, maybe a sodium plus and a chlorine minus are going to come together because of their opposite charges, and it is the strongest type of intermolecular force. Right, when you think about it, you know, think of salt. Right, you really, in a realistic fashion, you can't melt salt. I mean, yes, technically you can, but it melts at like 1,000 degrees Celsius. So in by all real, you know, purposes, you can't really melt salt without putting in incredible amounts of energy. And this is why, right here, because of the fact that the intermolecular forces between something like sodium chloride or calcium nitrate, maybe not calcium nitrate, calcium chloride, you know, potassium iodide, any sort of ionic compound will have incredibly strong intermolecular forces. And really, this is not one that will show up on the exam too heavily in terms of intermolecular forces, due to the fact that really it's just an ionic compound. But it's still important to know that it's the strongest type of force. All right, so then there are ion-dipole, right? So the one example that I can really think of with this is when you dissolve an ionic compound in water, right? So you have your ions floating around in this water, right, like this, and then you're going to have water molecules, right? So you have your oxygen here, and then you have your two H's, right? And basically, because of the fact that hydrogen, or that that water's polar, right? You have a negative end here, and a positive end here, right? We're going to see that when you dissolve an ionic compound in water, the water molecules will basically pull apart that ionic compound and orientate themselves around the ions, kind of like in this kind of fashion, where you have the actual dipoles, where you have the dipoles facing in the direction of the ions that they will, that they would rip apart. So you have the positive end. No, I was right the first time. I always kind of mess up the orientations, but it's really just line the positive end up with the negative end and the negative end up with the positive ions. So it kind of looks like this, and you're going to have 4 per ion. I won't draw them in right now, but really that's what ion-dipole forces are. And again, that's not really that shown in the exam due to the fact that it's just dissolving something in water is the general case. So then we have dipole-dipole forces, right? This is where we start getting into actual real intermolecular forces, right? Let me just try to maybe move these off to the side if I can. There we go. Right, so let's first start at dipole-dipole forces, right? So dipole-dipole forces will occur when we see, when we find polar molecules, right? So for example, if we're looking at something like water, right? We just talked about H2O, right? We have H, and then an oxygen. And we see that that oxygen is a lot more electronegative than the two hydrogens. And so it's going to pull those electrons like this, right? And because it's not symmetric, we're going to see I can never draw this, a partial negative charge over here. We're going to see two partial positive charges come together right there. So what we see is that we have like a cup of water, right? We see that we'll find the negative end of another water like this, right? We have the positive ends on the hydrogens. We'll see them kind of have it's not going to be the same as an ionic force because of the fact that these are just partial charges. They're not full positive negative charges, but we'll see attraction between the molecules. And these cause, and the varying strengths of these tend to change the properties of that liquid, right? How tense is the surface? How viscous is this fluid? What's its boiling point compared to other things? What's its melting point compared to other things? Vapor pressure, a bunch of other properties are really defined by just this strength right here. And you'll see dipole-dipole interactions in every single polar compound. So for example, let's take a look at something like, I'm trying to think of just an example of a polar molecule, maybe chloromethane, right? So we have chloromethane. I know you don't know you might not know why this is called chloromethane. It's not important. But we will see chlorine pull electrons this way, and then maybe we'll see carbon pulling this way. And so we'll have maybe a net negative charge here, and then some positive charges maybe on the hydrogens. I'm not sure what the actual like polar bits look like, but then we'll see that when we have another chloromethane, we'll see interactions then between, say, the negative chlorine, right, and the positive other ends of the other molecule. And so that's really what dipole-dipole forces are all about. Basically just two polar molecules and opposing charges lining up, right? Okay, so now let's talk about hydrogen bonding. So hydrogen bonding is really just a stronger, fancier type of dipole-dipole interactions, right? They are actually stronger than dipole-dipole interactions, and I'll explain why. But they're basically just dipole-dipole forces between hydrogen, and the three main ones are nitrogen, oxygen, and fluorine. Right. So, for example, if I can pull it up, on the free response questions last year, they asked us a question about this, and if I can find it, I'll show you it. Here we go. So they wanted us. So I'll pull this up. They showed us a molecule called urea. It was dissolved in water, and it was and basically they want us to identify a hydrogen bond. So really all you got to do is just identify a hydrogen bond between a hydrogen and something, either a nitrogen or an oxygen. So for example, and there's no fluorine. So for example, that would be a valid answer, right? Between that hydrogen and that oxygen. So that's an example of like an AP style question. Something like this would also be applicable. Or I wonder if this might be applicable. I am not too confident on that, but these two definitely. Right. And then London dispersion forces are for when you don't have a polar, molecule. So for example, take methane, right? This is not polar. However, because of the fact that the atoms are moving around and the fact that they are still kind of random in a way, the electrons might be shifted toward one side at a particular moment, right? So for example, if we see the electrons are kind of shifted over there, and we'll get kind of a negative charge, just a very instantaneous partial negative charge. This doesn't stay at all. They're called induced dipoles, and they're basically what what defines London dispersion forces. It's basically between these induced dipoles forces kind of forming and incredibly weak intermolecular attraction. So that's why, for example, methane at room temperature is a gas, right? Because of the fact that it really has super weak London dispersion forces. So that's really everything not everything, but that's a lot of what you need to know regarding intermolecular forces in terms of what they are. So sorry, I know that took a good while. All right, can you explain solubility and the Beer-Lambert law? All right. So I know the Beer-Lambert law isn't the most important concept. It's definitely in the curriculum. And the formula for it is that A is equal to ABC, where A is equal to absorption. Yeah, it's used so little that I don't even remember what it is. A is equal to molar absorptivity, B is equal to path length, and C is equal to concentration. Basically, what Beer's law has to do with is a type of experiment called spectrophotometry, right? And what spectrophotometry is basically, here, I'll try to find an actual diagram because I'm not an artist. Here we go. Just a picture of A equals ABC. Let me just give it a minute to try to find it. Here we go. There. So basically what happens is when you have something dissolved in water, right, what will happen is that some of it will be absorbed by the actual atoms or actual molecules dissolved in the water. So there we go. Right, so we have this L would be our B, right, our path length. Our C would be our concentration of whatever's in here. And the absorption is basically what percentage of light is actually eaten up by this compound, right? If I get, this much light to go in and only this little bit came out, what happened here? So for example, it's really only applicable when you have colored solutions. So for example, you might use spectrophotometry to find the concentration of, we actually did this in our AP Chem class last year. We used Beer's law to find the concentration of dye in Gatorade, for example, right? You have this red, Gatorade, you run some red light through it, how much red light was actually absorbed by it. Or I guess you would want to, we launched, it was green light at it because you want whatever will be absorbed, right? So then we launched green light at it, right? And then what came out was maybe, I forget the actual results, but it maybe looked something like this, right? And you plug it into a special machine called a spectrophotometer for the exact reason of you can't really do this qualitatively. But that's really how Beer's law generally works, right? You have some light going through, it's absorbed, and then whatever's comes out, you can find the absorption with it. Really, you're not going to see A equals ABC tested very often, let alone with the formula. It's on the exam, so you should know it, but it's not the most, I'd probably list it as one of the lesser important details in the course. All right, how do I find the limiting region or limiting reactant? So I'm going to do this by actually going through a problem because I don't really know how to explain it without a problem. Here we go. So there's a problem. Basically, all it boils down to is just using mole ratios and stoichiometry to actually define how much you're going to run out of first and how much you're going to what you're going to run out of first and what you're going to have left over. So for example, this question is asking how much zinc chloride can be produced from the reaction of 2 moles of zinc, right, and 3 moles of hydrochloric acid, and which is the limiting region, right? So we know we have 2 choices for what could be the limiting reactant, zinc or hydrochloric acid. And you might be looking at this, it's on the 2008 multiple choice, had like 3 or 4 questions. Huh. Yeah, and Beer's law, are you talking about Beer's law, Peter? Just to kind of clarify. Because I know it's on the exam, it's just not the most, you could probably skim by without really knowing it, but, you should still, if you can, know it. So really, you might be inclined to look at this and say, oh, well, we only have 2 moles of zinc compared to 3 moles of hydrochloric acid, so therefore we're going to run out of zinc first. But remember, for every mole of zinc, we need 2 moles of hydrochloric acid, right? That's what that 2 tells us. So really, we don't know just looking at this and looking at the raw numbers what's going to happen. So what we need to do is we need to take this 2 moles of zinc and convert it into moles of hydrochloric acid. And basically that will tell us that with these 2 moles of zinc, how much hydrochloric acid will we need? So we just do a little bit of dimensional analysis, right? So for 1 mole of zinc, we get 2 moles of hydrochloric acid. And we find that we actually need 4 moles of hydrochloric acid to eat up that 2 moles of zinc, right? So what this tells us, essentially, at the end of the day, is that that our limiting reactant, we're going to run out of hydrochloric acid first, right? We need 4, we only have 3. So that's how you find the limiting reactant. So I'm going to kind of highlight it, I guess, if that makes sense, just like this. So that's our limiting reactant. So from here, it just becomes a relatively simple stoichiometry problem, right? Because now we know what we're going to run out of first. So that's what we use for all of our computations, because it's what limits the reaction. So we take 3 moles of hydrochloric acid, and we just multiply it by the mole ratio. So it would be, we're looking for zinc chloride, so we want 1 mole of zinc chloride all over 2 moles of hydrochloric acid. God, that is handwriting. And so that'll give us 1.5 moles of zinc chloride. So that's really a general overview of what it looks like to do a limiting reactant problem. It's really a matter of just really, this is the one step that's different from others, right? Converting and comparing the numbers, really. All right. Now we had one more question. How do you do a redox titration equation using equilibrium or stoich? All right. I'm going to also try to find a redox titration problem, because of the fact that I really don't have much experience with redox titrations, and they're something that came up pretty frequently on the exam, which kind of makes me mad. But it's really just a matter of just using general, unless you're given equilibrium constant, to do a titration, right? So, for example, let's kind of look at this analogously to an acid-base titration, right? The type of thing we're both used to. You know, when we're looking at redox titrations, we don't have like weak oxidizers and strong oxidizers. It's not something that happens. And so we just assume that redox reactions just go all the way forward. Because when we're looking at a redox reaction that that does go forward, we're really going to have an E naught value that's positive. Therefore, just by looking and saying that K is equal to NFE, I think it was? Or was it G? It was delta G. Okay. So delta G, right, is equal to negative NFE. So therefore, delta G is negative, and therefore K is going to be positive. So really, and greater than 1, I should say. So we know that by looking at that step-by-step thing, that really it's just a matter of using stoichiometry. So really, when you look at a redox titration, don't get freaked out by seeing, ooh, titration, right? I know if you're looking for good practice with them, the free response question number 7 was a good one from last year. I didn't do well on it whatsoever, but it was a solid question looking back at it. All right, can you explain the structure of the test? So is it just multiple choice? It is not just multiple choice. I forget, I'm gonna look it up real quick because I forget the actual like numbers of questions and all that jazz, but it is multiple choice. It's kind of the same as most other exams, right? You have multiple choice and free response. So I'm trying to find the actual, here we go. So there are 2 parts, right? The multiple choice and the free response. So for the multiple choice, you will get 90 minutes to answer 60 questions. Right? I'm gonna make myself big again. Right, so you'll get 90 minutes to do 60 questions. And the 2 sections are each just 50% of your score, so it's good. So really in it, you're just gonna be answering normal multiple choice type questions. Some of them might ask you to do a calculation, but you are not allowed a calculator on the multiple choice portion. And so they're going to give you easy numbers. And so that kind of gives you an indication of like, when you see a problem with numbers, you know it's going to work out in some way that it's going to simplify, or you're going to be able to do easy finger and toe math, as my teacher calls it. You're also going to have to kind of interpret models. It's going to be more the qualitative aspects of chemistry a lot of the time. I don't have many examples due to the fact that you know, students don't really have access to too many AP Chem multiple choice questions, but they're pretty widely available to teachers. So your teacher, I know you, but so yeah, your teacher will be giving you a lot of multiple choice practice near the end of the year. I'm sure if you go to him and go, you know, hey, I want to do some AP practice, he will be more than happy to go through it with you. But that's kind of how the multiple choice works. And the free response, there are 3 questions that are long and 4 short. Right, there are 7 questions total. And actually, I will pull up the questions from this year. Hopefully, I'm allowed to, and show you basically what it looks like. Right, not to scare you, but to just show you, you know, this is what you're going to be expected to do. Those are the scoring guidelines. I'm so dumb. Yes. Here we go. If we just try to find them, there we go. So I'll show you basically what they look like, right? So here it is. Right? First, you get your periodic table. So you will have a periodic table, right? And this is the exact one that you will get on the exam, right? There are no names, so you do need to know chemical symbols, but they do give you molar masses, and that's really all you need. And really, you're not going to be dealing past like element 50, not even really. So it's really not super important, or it is really super important to know your periodic table. Then you have your formula sheet, right? And as of right now, you might not know half of these equations. I know you personally are kind of probably going to be covering this kind of stuff right around now. You've got your equilibrium stuff, your kinetics stuff, your gases and solutions, right? So here's the formula for partial pressures that we were going over. And then thermochemistry and electrochemistry. So for example, here's Q equals MC delta T. Here's the delta H, products minus reactants. And then you have your questions, right? So typically what they look like is they will give you some sort of situation, right? So here, the compound urea is used in chemical fertilizers, and that the structure of it is shown above. They're going to ask you, you know, what's going on with the bonds, calculate concentrations, you know, justify these answers and calculate these things. And they're kind of all different, right? This one has to do with like ionic compounds. This one has to do with dissolving stuff and equilibrium. They're all different, right? And then this is what a short question looks like. It's kind of 4 parts, quick, easy, just get through them, right? So really, they're not that bad. They're not as bad as you may think they are. So it's okay. So is it enough time, or did I have to rush? The multiple choice you typically have, if you know what you're doing, at least, which I know is a lot to say about some people, is you will have enough time. You'll have more than enough time. I remember I finished my exam with probably roughly like 15 minutes to spare after finishing. So I went back and checked my answers and like went to the bathroom and just kind of breathed. But no, the multiple choice is more than enough time. The free response, you really do. I mean, throughout the whole exam, you have to be moving, right? You can't sit there and take a drink and kind of take a quick and like, no, this is an exam where you're going to walk out of there pretty tired. You know, your brain's going to be moving a lot. But for the free response questions specifically, you want to get through those first 3 relatively quickly. But you want to take your time, right? You don't want to just be like, okay, I got to speed run through questions 1 through 3, and then I can take my time. Like, it's just the fact that 1, 2, and 3 are the longest, and so they're going to take you the most time, right? The typical short one might have 4 or 5 parts. The longer ones might have closer to double that, right? So it's important to get the longer questions done first, but also it's okay to jump around on the free response as long as you're writing your answers in the right spot. It's really pretty acceptable to write your answers, kind of go from question 3 to question 6 to question 3 to question 5 to 1, and just go back and forth between all the questions, right? So that's really something that helped me on the exam, is just jumping back and forth between questions. When I was, you know, when I would spend too much time on one question, I would say, all right, we'll come back to this, you know, and I flipped to question 4. It was actually question 3 that killed me. I skipped to question 4, did question 4, 5, 6, and 7, because those were all relatively easy, then came back to 3, and that I was rushing. I'll be honest with you. On the last one, I was rushing, but that's just because I got a question that just like, it killed me. There's if you look at them, the last half of question 3 was brutal. So yeah. All right. Any other questions? AP Chem, content, you know, chemistry, even just anything really. I'm happy to answer any questions you have. Maybe with Q1, 2 in 2018. What was that one? I feel like I've done those. Let me check. Definitely have done them. I did them with my teacher. That was I feel like I really liked your question 1. I really did. Yeah, your question 1 was great. It was just easy. Yeah, so like Liba, because I know where you and Joey, now that you've joined, hi. If you guys are looking for free response questions to do, I would say probably question 1 from 2018 is, oh my God, it's a perfect question for you guys. Yeah, no, you could do that entire question probably. So yeah, if you're looking for a good question to do, 2018 question 1, that's a perfect example. Wow. Right, and because I know where their class is, so yeah, and then question 2 is, yeah, question 2, it's just that titration question. It's really not that bad. Right, any other questions? I know, Joey, you just joined, so if you have any other questions, probably gonna be hanging out for the next like 20 minutes or so, or just as long as you guys have questions. So yeah, kind of give you guys another minute or 2. All right, if there are no more questions, I'll kind of hang out for another 2 or 3 minutes. You know, even just if you guys have anything to talk about just regarding AP Chem, there you go. Can you explain how to do a fusion? Oh boy, I have not looked at a fusion in so long. So let me try to kind of pretend I know what I'm talking about and Google as fast as I possibly can. So really, a fusion is, oh, I do know what a fusion is. Okay, we're fine. A fusion is when you basically have yeah, I remembered Graham's law of diffusion. I forgot my favorite thing. It was so cool. So Graham's law of diffusion basically says that the formula for it, and it's actually, I don't know if you have to apply it quantitatively on the exam because you don't get the formula for it, but it basically says that the square root of I forget if it's the moles of gas or if it's the molar mass. I want to say it's the molar mass. So if you have 2 gases, right? So if you have like a gas here, if you have a mixture of gases, right, in a little, you know, thing, and you have them escaping out, right? The rates of effusion of these gases, to compare them, it is the square root of the molar mass of gas 2 over the molar mass of gas 1 equals the, I don't know if it is actually velocity, but it's the speed of the first one over the speed of the second one. So basically the way a fusion, the way this really works is that you're able to qualitatively just look and see that that the inverse square root of the molar masses is going to lead to a relationship between the velocities. So if you have a really heavy particle versus a really light particles are typically going to move faster than our big particles. I think that's the conclusion Graham made. You know, Peter, if I'm screwing up here, please come in and roast me. But yeah, that's really Graham's law of diffusion. It's not the biggest topic on the exam. I don't even remember if it's in the curriculum anymore, but it's definitely something to note. All right. Which equations should we know that are not on the formula sheet? That's a really good question. Let me actually pull up the formula sheet so I don't start giving you stuff that is on the formula sheet. There are some that, I mean, any like equations that you're going to be using are going to be on here. There are a couple little things that you're going to really want to know that are just helpful. So the really big ones maybe that come to mind immediately, M1V1 is equal to M2V2, right? This is a really important one. This one basically is, I call it the dilution equation. For example, if we have, you know, 0.5 molar hydrochloric acid and we want to dilute it to a concentration of 0.25 molar, how much water do we have to add, right? We just use M1V1 is equal to M2V2. Right? Physics, which has 20. Oh God, that's horrible. I'm never taking AP physics then. Oof. It's all calculus anyway. Calculus is for nerds. So, right. So that's really one of another important one I would say is probably the combined gas law. So for example, if it'll be P1 V1 over T1 is equal to P2 V2 over T2, right? This isn't shown on the exam, but or it's not shown on the formula sheet, but it did come up last year, and I didn't use it, but I still got the question right by sheer luck. Basically, what you want to do is when something's held constant, you want to hide it from here, right? So let's say at a constant temperature, we're changing the volumes, right? And we're looking for change in pressure. Or if volume is constant, we're changing pressure with respect to time, right? We want to get rid of the volume. It's really just a good way of remembering the multiple gas laws. And I guess technically you would have N1 and N2, but you're never going to see this right here because I don't think that would work. So really this is one of the ones that you should know. Stuff regarding rate laws, it's probably good to know that rate is equal to K times some concentration to some order, right? And then times some other concentration to some order. That's not really a formula, but it's something that you need to know how to write out. You need to know how to write a rate law in such a way that you'll be able to do. Through here, there aren't many that they don't give you, honest to God. When you get to electrochemistry, things like the Nernst equation, which I do not have memorized, it would be helpful to know. Other ones you can kind of extrapolate. Yeah, no, there really isn't much that they don't give you. They even give you like the stuff for KP, KC, KA times KB is equal to KW. They tell you what PKA and PKB means. Yeah, no, they really don't give you much, or they don't. You don't need the Nernst or the Arrhenius, right? I know my teacher personally, and I know there are a couple of people in here who have my teacher. He does teach the Nernst equation, and you're going to have to know how to apply it. When he teaches it, honest to God, just zone out. You're not going to need to know it outside of having to know it for the test, like for your testing class. So really, it's not important to know the Nernst or the Arrhenius equation, even though he's going to teach you guys because he's a god. All right, so I know you see a couple of people joining. So really what we're just doing, any questions that you guys have about AP Chem, drop it in the chat, drop it in the Ask a Question box, and I will be happy to be of assistance. Oh my God, who is screaming? Jeez, my brother has friends over, so if you guys hear them in the background. All right. Could you explain the phase diagram and the heating curves? Of course. Those are actually some of my favorite topics in AP Chem. The phase diagram you actually don't need to know specifically for the exam, but it's one of those things that, like, even if you don't need it for the exam, you need to know it. So let me just pull up this whiteboard again. There we go. Right. So a phase diagram, right? So on here we have pressure, and on this axis we have temperature. And I just want to make sure I draw this right. We basically see, okay, it was going to be red anyway. We see a 3 lines. We see a line that looks like this. We see a line that looks like this, and then a line that looks like that, right? Or it's going to look something like this. So really, what this tells us is at which temperatures and pressures are we going to have solids, liquids, and gases, right? So we have solid, liquid, and gas. And then after this point, we see this actually go like that, and asymptotically kind of go like that because of the fact that there's at some temperature that you've broken those intermolecular forces to shreds. You're not able to you're not able to get back to a liquid, and that's called the critical point, right? Another notable point on a heating curve, or not a heating curve, on a phase diagram is right here. This is called the triple point. It's basically where you're literally at a solid, liquid, and gas at the same time. If we have time at the end, I'll definitely try to pull up a video of the triple point of water. It's pretty interesting because you see water both freezing, boiling, and at liquid at the same time. It's really something to see. And if you want, just Google triple point of water. There's a YouTube video of it. It's freaking cool. Then heating curves, right? What heating curves show you is basically the energy changes that have to do with evaporation or boiling or melting, right? So basically what it looks like is we see energy on this graph, and we see, I think temperature on this graph, right? So we see first, right, we have a solid, and we're starting to heat it up, right, and the temperature increases. And then we're going to see for a short time, right, that the temperature is going to go constant. It's going to increase again. It's going to go constant again, and then it's going to go into the gas phase, right? Or this is the amount of heat added, right? So energy added, so put in, right? So really, you might be wondering, so this is where you have when you have a solid, right? And this is the point where the solid begins to melt, right? And what this is basically what's called the it has a name. Basically energy that you have to put in order to actually melt something or freeze something in the opposite direction, right? Same thing here, right? When you get to this point, you start to evaporate, right? You're not fully evaporated, but you're just at the right temperature. I can't write. Wow, that was horrifying. Right? And then here you're finally at gas, right? And what this is, that's the heat of, there's two names. It's the heat of fusion and something else. Heat of fusion and, God, it's leaving me now. Here we go. It's the heat of fusion, right? So when we go from solid to liquid, and then heat of vaporization when we're going like that. So really what it tells you is you're really also going to only have to use this, vaporization, something like that, qualitatively. You're not going to be asked, typically on the AP exam, I'm not talking about your tests. You might on your test have to use something to calculate something, but on the AP exam, you really won't be asked too much about heating curves in general, but when you do, it's going to be qualitative. So yeah. All right, damn, you're like throwing me back to all the other stuff that I've forgotten from the past year. All right, any other questions? And we've got roughly 10 minutes left, and I'm happy to stay later if you guys need me to. So I'll kind of hang out for another minute, you know. There we go. All right, so any other questions, comments, concerns, anything? If not, I think I'll go, but you know, feel free to ask any other questions that you have. Not taken AP Chem, but not AP Chem, but have you taken or taking AP Micro? I am I'm self-studying micro right now, so I am right now in the middle of Unit 6. There we go. That's a good question. Here, Peter, I'll come back to your question in a bit. All right. So, what's one of the hardest AP questions that we should know how to solve? That's a really good question. It really depends on you. Like for me, I was really bad with kinetics. And so kinetics was where I was really weak. But I know for most people, the hardest types of questions are acid-base titrations, right? And I won't go into really how to do them because I doubt that you're at acid-base equilibrium right now. But basically what it has to do with is measuring the pH as you add a weak acid to a base, or a weak base to a strong acid, and seeing how, for example, like where we might see equal moles of acid and base, where we might see a buffer, where we might see the what's called the equivalence point, when we have equimolar quantities of acid and conjugate base, for example, right? And so it's something that you really need to go more in depth to when you start talking about acid-base equilibrium. But yeah, I mean, there's really no hardest question because, you know, for me, like titrations were pretty simple for me because of the fact that they kind of just clicked with me, acid-base ones at least. I know kinetics is kind of difficult. Thermodynamics typically throws people through a loop, but then when they realize that it's just applying a bunch of equations, typically, it's not that bad. It really depends on you, honestly. I'm sure there are people out there who their hardest question is just solving for moles, for example, depending on who they are. So it's kind of a question that I can't really answer that effectively. All right. So hopefully that answered your question. So back to Peter. Yeah, so I am taking AP Micro. I'm self-studying it this year. Yeah, electrochem is tricky sometimes. Electrochem is definitely tricky. So yeah, I'm taking AP Micro right now. I'm right in the middle of Unit 6, so I'm almost done. So yeah, that's really kind of what's going on with that. And I'm already registered for the test, so I'm strapped in. All right. Any other questions, comments, concerns? I'm probably gonna go and take a look at a titration problem after this. You know, hope and pray that I still know what I'm doing. Whew, jeez, my eyes. All right. So there are so many perfect competition curves. I mean, it depends on the year you took the exam. I know I've seen ones on monopolies, ones on perfect competition. So yeah, it definitely depends on your exam as to how much you see perfect competition. But perfect competition is pretty easy because it's just demand equals marginal revenue is equal to the price. So it's not really that hard to draw the graph for a firm. especially because you just draw the supply and demand market. We're spending 5 days on perfect competition. Oh my goodness, I did perfect competition in like 3 days. Just because I did cost curves one day and perfect competition the next, and it's just a graph. And once you understand like ATC and MC and looking for where MR equals MC, you can really do any market structure. It's kind of the same thing. All right, back to AP Chem. Any other questions regarding AP Chem or anything relating to it? Oh my God, why is my brother screaming? Okay. Right. So if there are no more questions, I think I'll just sign off for the night. I know I'll be back. When is it? Someday. I have to check the date. To do another stream, a content stream, not an AMA. But I'll be doing these AMAs kind of monthly. So if you guys have more questions, feel free to. I know for those of you who know me, feel free to. Oh, there we go. We have a question. All right. Any tricks for free response questions? I can't really think of any because of the fact that those questions are they're not like, I know Joey, you took AP World, and with that, it's a very standardized thing, right? Your questions will be different, but you know exactly how to format things. With the AP exam, they can really throw whatever they want at you. Time management, careful use of your calculator, paying attention to sig figs. That's something that'll get you sometimes. I didn't whatsoever. I forgot sig figs and just rounded everything to the hundredths place. And just not getting tripped up on what can be a simple question, right? By the end of the year, you'll know so much advanced chemistry that you'll kind of forget about the basic like Q equals MC delta T stuff. And so you'll see a Q equals MC delta T problem and be like, oh, this is clearly an equilibrium problem, or oh, this is clearly an acid problem. And it's like, no, it's just a regular problem. And so not complicating things and not making things more verbose than they need to be is really something that I struggled with. For you specifically, Joey, because I know you in person, your teacher, I'm not going to name him by name, but your teacher will be running free response question review sessions around March, April. So definitely go to those. They're going to be on Saturdays in the mornings. I'm going to try to see if I can help out with those too. What else? I know if you go to him right now with a free response question, you say, hey, I have this, help. He'll be more than happy to help you. A lot of stuff, combined stuff for multiple units. Yeah, exactly. Yeah, Peter, you're correct. Break it down into what you just need to answer. You're going to be seeing, there was a question last year where it went from like, intermolecular forces to a Lewis dot diagram to hybridization to like, energy changes and equilibrium. Like it was jumping around. And so situating the questions in terms of their topics is really a good skill to have regarding AP chemistry. So hopefully that answered your question. I know with your teacher specifically, you'd really go to him if you want any specific free response question from your teacher, at least. I'm also more than happy to help you out with the free response question. All right. Any other questions? Looks like we're kind of winding down here. Is there any other questions? Kind of give you guys another minute. If not, then I guess I will, sign off for the night. Last time I said that's when I asked a question. So yeah, it looks like, we're reaching around an hour, kind of time's up. But I mean, if you still have a last minute question, kind of get it in. So yeah, it looks like we're kind of done. So so I will be doing more streams in the future. Feel free to kind of keep track of what Five is doing with their streams. Definitely kind of try to attend as many as you can when they're live. And I will, see you all in the